Let us master the strategies of solving related rates problem in calculus and enjoy the journey of learning with Anil Kumar. Thank you. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. We are going to take many examples based on related rate of change in this particular video, and I hope it will give you confidence of solving such difficult questions. In case you want to learn directly from me, feel free to send an email on globalmathinstitute@gmail.com. Our students are right there on the top, getting excellent marks and admission to the best universities. Well, the question here is, a container is made up of a cylinder and a hemisphere as shown in the diagram. At the time when the radius is 6 centimeters, the volume is 684 pi centimeter cube. The radius is changing at the rate of 1.5 centimeters per minute, and the volume is changing at the rate of 1800 pi centimeter cube per minute. Find the rate of change of height at this moment. You can always pause and answer the question and then look into my suggestions. So, we are given this diagram where that is the cylindrical part, and as you can see, the radius of the cylinder is given to us as r, which is also the radius of the hemisphere on top of it. Important thing which we need to note here is that radius is changing, right? R is changing. Since we are given the rate of change of radius is, which is dr dt, is 1.5 centimeters per minute, right? So we are not writing units here. Height is this height which we are considering, height of the cylinder. Correct. It's kind of an ambiguity, but we'll just put height of the cylinder. So radius is changing and height is also changing, right? We need to find dh dt when radius is equal to 6. That is what we need to find from all other things given to us. So first, at this condition where r is 6, we should be in a position to find the height, right? Okay, which we can because we are given that if the radius is 6 centimeters, volume is 684 pi centimeter cube, right? Okay, so now let's write down an expression for the volume of this silo. So volume is volume of the cylinder, which is pi r square h, plus volume of hemisphere. Hemi means half of sphere, which is 4 by 3 pi r cube. Correct. So we could write this as volume as pi r square h plus 2 by 3 pi r cube. Since the volume is 684 pi, let's write down. Radius is 6 for us, so 6 square. Height we need to find plus 2 by 3 pi 6 cube, right? So we get an expression where everything is known to us, pi's will cancel, right? And we can now find out the value of h. So as you can see from here, let me rewrite final calculation. 684 equals to 36 h plus 2 times 6 cube. So let's multiply. 6 cube is 216, right? We'll multiply that by 2, which is 432. Correct? Divide by 3. We have to do divide by 3 also. So 432 divide by 3. 144. Correct. So 2 times 6 cube divided by 3 gives us 144. Okay. So 36h equals to 684 minus 144. So 36h is 0, 4, 5. And h will be 540 divided by 36, which is 15, right? So we get the height in this particular case at the instance when radius is 6. Okay, so if radius equals to 6, height is equals to 15. Very important. We got that. Now we'll move further. Find the derivative with respect to time and then also find the rate of change of height. Perfect. I hope it is absolutely clear up to this point. Okay, so height of 15. So here what I've done is I've written everything which is given to us. Radius is 6 centimeters, volume 684 pi centimeter cube, drdt 1.5 centimeters per minute, and we also find height as 15 centimeters. dv dt 1800 pi centimeter cube per minute, and we need to find dh dt when r is equal to 6. Perfect. Great. Now let's begin with the volume formula, which is pi r square h, that is the volume of the cylinder, plus half of 4 by 3, so 2 by 3 pi r cube. So now we need to differentiate with respect to time. Remember, both r and h are changing, so we need to apply product rule for the first term. So what do we get? We get dv dt equals to derivative of this. So you can say, let me first write pi is a constant, right? So pi is a constant. Derivative of r square will be 2r dr dt, right, times h, plus derivative of h. We have pi r square dh dt. So what we have done here, we have applied the product rule, right? Differentiating further, first with respect to, first we differentiated r square, then h. The next term here, differential, is 2 by 3 pi times 3r square times dr dt, right? Implicit differentiation. So we have an expression. This can be simplified. Okay. So we can now substitute the values given. dv dt is 1800 pi. So we are substituting the values. 1800 pi equals to pi times 2 times r of 6. dr dt is 1.5 times height. Height is 15. We calculated. Plus pi. Actually, we could have cancelled pi, but anyway, let me rewrite. Pi r square is 6 square. dh dt we want to find, plus 2 times 3. 3 cancels, right? 2 by 3 pi r cube, 3 r 3. So we get 2 pi 6 square times 1.5 for dr dt. Correct. Now let's cancel pi's, right? We could have done it earlier also. Great. So dh dt is the term here. We'll write down all the numbers. 1800 equals to, let's multiply. So we have 2 times 6 times 1.5 times 15, 270, plus 36 dh dt. And here we have plus 2 times 6 square, which is 36, times 1.5, 108. So from here we can, from 1800, subtract 108 and 270. That will give us 36 dh dt, correct? So this is 1800, take away 108 and take away 270. That gives us 1422, which is 36 dh dt. So from here we can find dh dt equals to 1422 divided by 36. 79 by 2, or 39.5. Units being centimeter per minute. Is that clear to you, right? A lot of calculations required. However, the critical part which I find is that when you do implicit differentiation, you have to differentiate R also for cylinder, right? I think otherwise it was not so difficult. Now let us take the next example. We'll discuss related rates of change application. We have taken a very important question, which is, we'll find related rate of change of a sphere in a case of a sphere. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. Let me thank all the viewers and subscribers for watching my videos, posting excellent comments, and sharing brilliant questions. These questions help all the viewers and subscribers to do extremely well. It is your website. Keep sharing. The question which we are going to discuss is, volume of a sphere is increasing at the rate of 100 centimeter cube per minute when the radius is 10 centimeters. Part A, find the related rate of change of radius at this instant, and part B is, find the related rate of change of area when the radius is 10 centimeters. You can always pause and then answer the questions. At the end, check your solution. Right. So, when we're talking about related rate of change, it is differentiation with respect to time. Let's write down what are we given. So, we are considering a sphere where the volume is increasing at the rate of, so dv dt is 100 centimeter cube per minute. The instance at which we want to work is when the radius is equal to 10 centimeters. And we need to find related rate of change of radius at this instance, means dr dt. Basically at r equals to 10. This is what we need to figure out. First step is always write down what is given and what you need to find. Second step, write down the related equation. We're talking about volume. Volume of the sphere is 4 by 3 pi r cube. We are given dv dt. We want to find dr dt. So we are going to differentiate with respect to time. So we get dv dt equals to d dt of 4 by 3 pi r cube, which is 4 by 3 pi is a constant r cube, apply the power rule. So we get 3 times r square. But r is a function of time. So we should be writing here dr dt. So that is the implicit differentiation which we have just done. So from here, we can find what is dr dt at the given instance. So at a given instance, we know that the rate of change of volume is 100. So let's put in the values, right? So the values are 100 for dv dt and 4 by 3, 3 and 3 cancel. So we have 4 pi r square, right? So 4 pi r square, r is 10, 10 square, and dr dt, correct? Dr dt. So that gives you 100 divided by 4 pi times 10 square, which is also 100, is dr dt, rate of change of radius with time. So 100 cancel. So we get dr dt as equal to 1 over 4 pi, right? So this form is good enough. Units will be centimeters per minute. Is that clear to you? So that is how we are going to do part 1. So we got dr dt as 1 over 4 pi. I hope all the steps are absolutely clear. Now let us do part 2. So we just found that dr dt is equal to 1 over 4 pi centimeters per minute. We are given dv dt as 100 centimeter cube per minute. R is 10 for us. Now to find the rate of change of area, what is the area of a sphere? Well, the area of the sphere is 4 pi r square, correct? So rate of change of area will be dA dt. Differentiate with respect to time. So we get 4 pi and derivative of r square, let me write d dt of r square, right? Which is 4 pi times 2r times dr dt, correct? Now, dr dt at t equals to at r equals to 10 is already given to us as 1 over 4 pi, right? So we'll substitute these values. So what do we get here? 4 times 2 is 8 pi, radius is 10, and dr dt is 1 over 4 pi. Is that clear? So now you can cancel. 4 goes 2 times, and what we get is 20. Unit area centimeter square per minute. Makes sense, straightforward. So to find rate of change of area, use area formula, which is A is 4 pi r square for a sphere, right? And then differentiate with respect to time. We earlier found the value of dr dt. Use that to get the solution. I hope it makes sense. It's a huge application of calculus. We'll have a very simple question here, only to understand the concepts. The playlist has 100 more videos for you to explore and master these strategies. In case you want to learn directly from me, feel free to send an email on globalmathinstitute at gmail.com. Our students are right there on the top, joining the best universities. The question here is related to spherical balloon rate of change of radius. Well, you'll see that the volume becomes surface area when you find the derivative at the end of this particular derivation. The question here is a spherical balloon is being filled with air at the rate of 3 meter cube per minute. Find the rate of increase in radius when the volume is 36 pi meter cube. Now, in all the related rate questions, we are actually relating two or more parameters and then differentiating it implicitly, normally with respect to time. So that is the key while we are going to solve these questions. We should always begin with the basic formula. We're saying spherical balloon is being filled with air at a rate of 3 meter cube per minute. It means volume, right? So 3 meter cube gives you an idea. Meter cube is volume and per minute is time. Makes sense, right? So that is given to you as 3 meter cube per minute. So now we are looking at a sphere, as you know, and change of volume is what we are looking into. So we should know what is the formula for volume of a sphere, which is 4 by 3 pi r cube. You see how the things are related, right? Now, if I differentiate with respect to time, which normally we write like this, differentiate with respect to time, only t or time, then we get dv dt equals to d dt of 4 by 3 pi r cube. Now 4 by 3 pi is a constant. So therefore, we get 4 by 3 pi outside the bracket. R cube derivative with time will be 3 r square. Now r is also a function of time. It is changing with time. So therefore, we need to still differentiate r with time, correct? So it will be dr dt. You see, so we have dv dt in terms of dr dt. Perfect. Now if you see, we are already given dv dt. Radius we need to find dr dt, right? One more information is given, which is find the rate of increase in radius when the volume is 36 pi meter cube. So at this instance, when the volume is 36 pi meter cube, what is the radius? This is what we need to figure out. So okay, so the volume is 36 pi and it is related with radius 4 by 3 pi r cube. So cancel pi and pi. So r cube is equal to 36 times 3 divided by 4. Perfect, right? 36 pi is the volume, 4 by 3 pi r cube. So we'll multiply 36 by 3 over 4. So we get r cube now, which is 9 times 3, 27. Or radius is cube root of 27, right? Which is 3. So we know the radius when we want to find rate of change of time. So now the alternative for you is you can rearrange the equation or just substitute the values given and then find dr dt. So let's substitute the values. We know dv dt is equal to what? dv dt is given to you as rate of change of volume of 3 meter cube. So I'm writing 3 for that. And we got 4 by 3 pi. And this 3 also I'm cancelling now, correct? R square means 3 square. And only thing left is dr dt. Do you see that? So we have 3 by 4 pi, correct? And then this is 3 square, which is 1 over 9, equals to dr dt. Makes sense, correct? And this rate of change is when volume is equal to 36 pi. At this instance, radius is 3. So we have substituted those values. Perfect. And we are going to find what is dr dt now. So simplifying, 3 goes 3 more times. So we get our answer, which is dr dt equals to 1 over 12 pi. Radius being measured in meters and time in minutes. So it is very important to write down the units. Perfect. So I hope the concept is absolutely clear. Based on this, there are many questions in the playlist. I'd like you to go through them and then some more complicated questions. These are very important applications from test point of view, and in our playlist, we have got more than 100 examples. You can watch them and master these strategies. Here, we'll discuss how do we work when we have a conical pile of sand. Sand is being dropped on the ground at a steady rate of 9 pi centimeter cube per second and forms a conical pile whose height remains equal to half the diameter of the base. At what rate is the height increasing at 8-second mark? Let's try to visualize. So let's say sand is being dropped and it forms a pile like this, correct? So this is the sand pile. Now this is relatively simple question since we have already given relation between the radius and the height. Height is half the diameter means we are given that height at any instance is equal to diameter by 2 or the radius of the pile. So let's say if this is the height, right? And we're talking about this conical thing, and that is the radius. So the radius and height are related with the given condition to us. We are also given that sand is being dropped on the ground at a steady rate of 9 pi centimeter cube per second. It means the volume, right? So the volume is increasing with time at the rate of 9 pi centimeter cube per second. Now, we want to know at what rate is the height increasing at 8-second mark. So if t is equal to 8 second, what is going to be the volume? So then the volume will be 9 pi times 8, correct? So that is going to be the volume when we are really interested in finding all the parameters, at what rate the height is increasing. So we want to find the rate of change of height with time when t is equal to 8. So this is what we need to figure out. So I hope the situation is absolutely clear, right? Now let's write down the related formula. After all, what is volume? So volume is 1 by 3 pi r square h. Since r and h are same, we can rewrite this as volume is 1 by 3 pi h square h, which is volume is 1 by 3 pi h cube. So we have a formula in terms of h itself. And now we can differentiate with respect to time. Since height and radius both are increasing with time, the volume also. So that is implicit differentiation. Let's do it. So once we do that, we get dv dt equals to 1/3 h cube, so 3 times pi is a constant, h square dh dt. So we get dh dt, which we need to find. Now, we also know that when t is equal to 8, at this time, what is height? That we should know, right? Because h square is there. So when the volume is 9 pi times 8, which is 72 pi, if that is the volume, and this is the formula for volume, we can find what height is, correct? So we'll use this. 9 pi 8 is 1 by 3 pi h, right? So 9 pi times 8. I'm writing 8 at present, not multiplying them is equal to 1 by 3 pi h cube, right? So you can cancel pi and pi, see it becomes much, much simpler, and multiply by 3. So you get 27 into 8 is h cube. So cube root of this is what height is. Cube root of 27 is 3 and of 8 is 2. So we get height as 6. You get the idea. So we know the height. We have this particular formula right there that dv dt is equals to 1/3 will cancel pi h squared dh dt. Is that clear to you? We can substitute height equals to h and find dh dt. Correct. So we'll do all the calculations in the next page. Correct. So basically what we did was that we found that the volume was 1/3 pi h cube since r equals to h, right? And we wrote dv dt as 1/3 into 3 will be just 1 pi h square dh dt. And now we are going to substitute the given values. dv dt, volume rate of change is 9 pi, right? So we're going to write 9 pi. H we figured out is 6 square. And we need to find dh dt. Makes sense, right? So if you derive as we have done, you will clearly understand what is going on and how do we solve such questions related to related rate of change. And now it's a question of reorganizing and finding dh dt. So dh dt. Remember the instances when t is 8, correct? Pi and pi you can cancel. And what you get is 9 over 6 square, which is 36. And 9 goes 4 times, so 1 over 4. So that is the change in height, unit being centimeters per second. Do you see that? So the change in height at the instance when time is 8 is 1/4 of a centimeter per second. Perfect. So I hope you have understood the whole strategy. Feel free to write a comment, share your views. In this video, we are discussing about a ladder and trying to find the sliding rate related with the dimensions of the ladder. The question here is, a ladder 25-meter long is leaning against a wall. If the bottom of the ladder slides away from the wall at a rate of 3 meters per second, how fast is the top sliding down the wall when the bottom of the ladder is 15 meters from the wall? First step always is to sketch a diagram. So let's say that is the ground, and this is the wall. The ladder is shown, which is given to us as 25-meter long. And the instance is when the bottom is 15 meters away from the base of the wall. If the bottom of the ladder is sliding away from the wall, right, in this direction, then let's call this as x and wall as y. Now both are functions of time as they are sliding with time, so we can always write this as x of t and y of t. But at the given instance, when 25 is the length, what is the value of the y value, right? So at this instance, we can find 25 square is basically equal to 15 square plus, let's call this as y square. Now in this particular case, it is 25 square minus 15 square square root, which is y. Now that is equal to 20. So the value of y is basically 20 at the instance we are trying to calculate the rate of change. Now, in this particular case, we are given that the x value changes with the rate of 3 meters per second. The ladder slides away from the wall at the rate of 3 meters per second. So that means we are given that dx dt is 3 meters per second. How fast is the top sliding down the wall when the bottom is 15 meters away? So we want to find what is dy dt when the value of x is 15. You get the whole idea. This is what we need to find. So in the given situation, we need to first write down how these parameters are related. 25 is constant, so we know that xt square, the horizontal distance, plus yt square should be equal to 25 square at any instance of time. Now at this stage, if I differentiate with respect to time, in that case I get 2 times x, right, dx dt plus 2 times y dy dt equals to constant derivative is 0. So from here we can find the value of dy dt, right? Isolating dy dt, you can cancel out 2's, right? 2 will cancel. So dy dt is equal to minus x dx dt. So this is y times, I can divide x by y. So I've rearranged the equation to write it. Dy dt is this. What we need to find is when x is 15, at that time dx dt is 3 meters per second. We have to find what is dy dt. So we can substitute the values dy dt when x is 15. At that time we get minus x is 15. The value of y we calculate initially as 20 and dx dt as 3. So that gives you 15. You can divide, and then dividing by 5, 5 times 3, 5 times 4, we get minus 9 by 4. Units being meters per second. Now negative means it is sliding downwards, correct? So how fast is the top of the top sliding downwards? It is sliding at the rate of 9 by 4 meters per second. Is that clear to you? Perfect. So the steps involved are write down the initial given conditions and then write an equation, differentiate with respect to time, substitute the values and get the answer. So I hope that is absolutely clear. Feel free to write your comment, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your valuable time and all the best.